Hey guys, welcome to day 26. We're doing bonding theories, in particular today, valence bond theory. Valence bond theory, and I'll abbreviate sometimes as VBT. A chemical bond is the overlap between two half-filled atomic orbitals. That kind of makes sense. The bonds form when the valence orbitals overlap. As you can see, the greater the overlap, the lower the energy, the stronger the bond. The valence bond theory treats these electrons as residing in quantum mechanical atomic orbitals. So let's look at an example first of H2s Hydrogen Sulfide. Hydrogen, of course, has an electron configuration 1s1, and there's two of them. Sulfur has electron configuration noble gas core of neon. Then it's 3s2, 3p4. So if I draw the orbital notation here, orbital notation of hydrogen, H, will have its 1s atomic orbital, and the other H will have its 1s atomic orbital. Sulfur will have its neon core, and then, of course, the 3s and 3p. Electrons in hydrogen, 1s and 1s. Sulfur, up, down, 1, 2, 3, 4. So bonding opportunities. Hydrogen has one bonding opportunity, each hydrogen, and sulfur has two bonding opportunities in the p orbitals. These orbitals right here, so these electrons will pair up and these electrons will pair up, and we have something that looks like this picture over here where there are two bonds. There's a bond, there's a bond. I don't know if you see that. Yeah, there's a bond, there's a bond on the p orbitals. And if you look at these axes, that's one axis. Another arrow here, and that's another axis. They're kind of off a little bit, but they're not going to work. So we're having an axis here and an axis here. Of course, there's a vertical one as well. So we have, let's just say, Y, X, Z. So that means on the PX of the sulfur and a 1s of hydrogen will work, and a PY of sulfur and a 1s hydrogen orbital will work. We expect 90-degree bond angles, and we get a 90-degree bond angle. It works out beautifully. Now let's look at methane, which of course is CH4. H again, 1s1. Carbon, 1s2, 2s2, 2p2. So if we look at the valence of carbon, I have the 2s and the 2p. Of course, hydrogen has its one electron like it did before. There's four of these. So there's four H that can pair up. And carbon has up, down, up, up. So when we look at carbon here, how many bonding opportunities does carbon have? Well, each hydrogen has its one bonding opportunity. The problem I have with carbon is that this is full, right? The 2s orbital is full. And if we look, a chemical bond is when the overlap of two half-filled atomic orbitals. So the full atomic orbitals are not gonna overlap. I technically only have two bonding opportunities for carbon. However, we know methane exists, and we know that there are four equivalent CH bonds. So something else has to be happening. It's just not going to say, oh well, we're going to have to modify our model to fit what we observe. That comes to the hybridization of atomic orbitals. So orbitals in a molecule are not necessarily the same as orbitals in an atom. Hybridization is a mathematical procedure in which the atom's atomic orbitals are combined to form new atomic orbitals. Hybridization is a mixing of two or more orbitals. However, it's not an all or nothing process. I don't have to mix them all, but in this example, we do. So this example, I have carbon. So we got my C orbitals. And they would be 2s and the 2p's. And right now we have up, down, up, up. What this is this magical hybridization. And again, this is a mathematical procedure. We're just using math to make 4 equivalent hybrid orbitals. 1, 2, 3, 4. And we're going to call them the 4 sp3 hybrid orbitals. So there's 1s and 3p, so we just call it sp3. Makes it easy. 1, 2, 3, 4 electrons. So we go from the left picture to the right picture. And so now we have 4 bonding opportunities, which is very important. And here are the combinations of those bonding theories. We left off right here with carbon, sp3. So now we, instead of having the s, the circle, and then the px, the py, the pz, we now have these 4 orbitals that look the same, and they're tetrahedral. sp2, 1s and 2p's, sp, just right, an s and a p combined. Trigonal bipyramidal is sp3d, and octahedral is sp3d2. Wonderful. So when we talk about our hybrid sets, these are for central atoms only. This is important. Our book says only central atoms hybridize. Is there debate about this? Yes. Where you have an organic chemistry instructor that probably tells you that the terminal ones do, most likely. For our class and our book says only the central atoms hybridize, so we're going to go with that. Number of orbitals. So how many orbitals do we need? I need 1, well actually we need 2 to start with, so it's always 2, 3, 4, 5, 6. Which means we have SP, 1s and 1p, S and 2p's, S and 3p's, S, 3p's and a D, and S, 3p's and 2d's. And the direction which they point, these are the electron pair geometries from before. Linear, trigonal, planar. We have tetrahedral. We have trigonal bipyramidal. And we have octahedral. So those are the direction in which they point. So the hybridization scheme is going to come right from the electron pair geometry. Not necessarily the molecular shape, but the electron pair geometry. Examples. So we have this graph, by the way. I forgot about the graph or the chart. I always do this. SP, SP2, SP3, SP3D, and finally sp3d2 for octahedral. So now we want to know the arrangement, the electron pair arrangement or geometry, or EPG. So BF3, what's the electron pair geometry? Well, if we don't know it by looking at it, which you're not expected to, then what would you have to do? It might be very wise to draw out the molecule. Count the valence electrons, which would be 3 for boron, plus 3 times 7 for fluorine, so that's 24 electrons. Who's in the middle? Well, it's not fluorine, so boron would be in the middle. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Is that okay? Well, fluorine has 8 and 8. Boron has 6. Boron does not have 8. But if we remember, elements before carbon, which boron counts, can have less than 8. And this is fine. So the electron pair geometry for BF3, boron trifluoride, would be trigonal planar, which means the hybridization then is sp2. Now, it's very important to notice, and I haven't said this yet, is that when I have sp2, I have 3 of the 4 atoms hybridized. So if I'm going to scroll back up for a second, we have what orbitals do I have? I have an s, a px, a py, and a pz. How many do I need? If I need 2 orbitals, having 2 orbitals is just going to be those 2. That means the py and the pz are still there, unhybridized. If I need 3 orbitals, that means the pz is still unhybridized. If I need all 4, then there are no orbitals left. However, if we have less than 4 orbitals on these nonmetal atoms, there will be availability to use the unhybridized orbital in bonding. That's very important. All right, phosphorus pentafluoride. Electron count. We have 5 for phosphorus plus 5 times 7. So that would be 40 electrons. Who's in the middle? Well, not fluorine. So F, P, F, F, F. Bond 2, 4, 6. Oh, I got a little carried right there. 6, 8, 10. Octets 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Is that good? Well, each fluorine has 8. What about phosphorus here? 2, 4, 6, 8, 10. Can phosphorus have 10? Oh, it's in the third period below? Yes. Check. Good. What's the electron pair geometry? It would be trigonal bipyramidal, which means the hybridization is sp3d. XeOF4. Electron count for xenon would be 8. Oxygen 6 plus 4 times 7. That's what? 42 electrons. Central atom. Well, it's not fluorine, not oxygen, Xe. 1, 2, 3, 4 fluorines. Let's bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32, 34, 36, 8, 40, 2 extra on xenon. Well, what's the electron pair geometry? That would be 1, 2, 3, 4, 5, 6 pairs, octahedral. Hybridization, sp3d2. Now, let's take a deep breath. XeOF4, is that the best Lewis structure for xenon with oxygen and 4 fluorines? How would you tell? Well, we have a tool in our arsenal here to talk about this, and that would be formal charge. What's the formal charge on the fluorines? Fluorine has 1, 2, 3, 4, 5, 6, 7. It brought in 7. All the fluorines are 0 formal charge. Oxygen, 1, 2, 3, 4, 5, 6, 7. It brought in 6. It's -1 right now. Xenon has 1, 2, 3, 4, 5, 6, 7. It brought in 8. It is +1. Is there a way to minimize that formal charge? Well, could we, if we double bond that oxygen, these formal charges go to 0 and 0. Can xenon do that, though? Well, it has 2, 4, 6, 8, 10, 12. 14 electrons. I don't know. Minimize formal charge. Our book says to minimize formal charge, so we're going to go with this. Did it change our answer? No. Does it change the shape? No. Does it change the hybridization? No. Does it change if it's polar or not? No. Does it change anything else in our class? It does not. So, book says to minimize formal charge. We're going to do it, whether or not we get more than 12 electrons or not. Hydronium. Let's do the electron count of hydronium. We got 3 times 1 electron for hydrogen, plus the 6 electrons for oxygen. Positive charge, we're going to -1. So we get 8 electrons. Brackets for the ion. Central atom, of course, is oxygen. You got 3 hydrogens. It does not matter how you put them around. Bond, 2, 4, 6. And then extra electrons in the central atom, 8. Is that a valid Lewis structure? Of course it is. 2, 4, 6, 8. Electron pair geometry would be tetrahedral. So therefore, the hybridization is sp3. What's the actual shape? The molecular shape is trigonal planar. Is hydronium polar? I know it doesn't ask, but I'm asking you, is hydronium polar? Well, sure is. It is top 5 electronegative atom in an unsymmetrical shape, so it is polar. ClO2-. Electron count, we got 7 for chlorine, plus 2 times 6, plus 1. So that would be what? 20 electrons for chlorite. Again, brackets. Chlorine would be in the middle. Let's bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Is that the best Lewis structure? Well, oxygen is -1. Chlorine would be 1, 2, 3, 4, 5, 6. Technically, no, it's not the best. You could double bond from one side or the other. Will that change anything? No, it won't change any of our answers, but let's do it to minimize formal charge, because that's what our book says. Electron pair geometry. This is 1, 2, 3, 4 pairs, tetrahedral. Shape. The molecular shape is, of course, bent. And then we have hybridization, sp3. Is this polar? Yes, it is. It is bent with oxygen on the outside. CO2. Electron count. 4 plus 2 times 6 would be 16 electrons. Carbon in the middle. Bond. 2, 4, 6, 8, 10, 12, 14, 16. Oh, double bond both sides. to minimize. Now we double bond both sides because now the formal charge is 0 for everybody. Electron pair geometry, that counts as 2 pairs. It's linear because it's 2 pairs. Even though they're double bonds, one of those double bonds is hybridized and one of those double bonds is unhybridized. So one of the lines is in an sp orbital, right? Because the hybridization is sp. And the other one is in an unhybridized p orbital. So you have 2 p orbitals here in carbon that are not hybridized. We'll get to a picture soon. The shape is also linear for the molecular shape. And then polar. Is this polar? Not polar. It is symmetrical. Symmetrical. SF6, sulfur hexafluoride. Electron count. Sulfur is 6. I want to use red. Sulfur is 6 plus 6 times 7. So that's 48 electrons. Middle, we use sulfur. So we got F, S, F, 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 F. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 2, 34, 36, 38, 40, 42, 44, 46, 48. There we go. Sulfur has 2, 4, 6, 8, 10, 12 electrons. Each fluorine has 8. Sulfur can have more than 8 because it's in the third period or below. So we are octahedral, which means we are sp3d 2. sp3d2. The shape is also octahedral. And this, of course, would be not polar because it's symmetrical. Even though it has 6 very polar bonds, it is a symmetrical shape. BeCl2. Electron count. We have 2 plus 2 times 7, 16 electrons. Who's the middle? Be, so Cl, BeCl, bond. 2, 4, 6, 8, 10, 12, 14, 16. What is that good? Well, can beryllium only have 4? Yes, it is a natural group 2 metal. However, it actually is a covalent compound. So our electron pair geometry would be linear. Shape is also linear because there are 2 pairs. So that means the hybridization is sp. Is this polar? No, it's symmetrical, so it's not polar.